Hey guys, this is Mrs. Harbin, and this is our last unit in our geometry review, our last lesson. And today we're going to talk about parallel lines, perpendicular lines, and pairs of angles formed by parallel lines, and all the information that can give us. Our whole biblical correlation for this unit has been based on Colossians 1:16 through 17, which says, "For by him all things were created, things in heaven and on earth, visible and invisible, whether thrones or powers or rulers or authorities, all things were created by him and for him. He is before all things, and in him all things hold together." And you've heard me say it plenty of times, but that includes math. It includes those rules and those patterns that are maybe not visible to the naked eye, but we know that they exist, as well as the visible patterns that we see. It includes all of the subjects that you study, the recording of human history, the laws of nature and science. These are all things that have been created by God for him and are held together by the order that he created and through him. Our objective for this particular lesson is to look at some of these patterns. Specifically, we're going to look at parallel lines, and you, the student, will interpret parallel, perpendicular, and intersecting lines, plus determine the measure of vertical angles based on the patterns that we know about parallel lines. So let's start with some basic definitions here. We know that lines are parallel if they are always the same distance apart. We can call this equidistant, which means mathematically they have the same slope. If this were on a Cartesian plane, we could prove it by finding the slope of each line, and they will never meet. So we can't tell that lines are necessarily parallel just by looking at it. Lines can sometimes look parallel and be off just slightly and end up crossing. We need to either measure the points at several different places along the line to make sure they're equidistant or find their slope. Intersecting lines goes back to the idea that an intersection is the point at which two or more lines touch or cross. Therefore, lines are intersecting when they cross each other. Those of you who have your driver's licenses, which I think everyone does by now, you guys know that an intersection is where two roads cross, and lines are considered intersecting if they cross or touch each other. When intersecting lines meet at a right angle, we have a special name for that type of intersection, and that is a perpendicular set of perpendicular lines. So a line meeting another one at a right angle or 90 degrees is said to be perpendicular to it. So if we were to name this line, line AB, and this line DF, we see that line AB is perpendicular to DF because they meet at a 90-degree angle. And many of our roads and our road systems are also perpendicular and meet at 90-degree angles. All right, now let's talk about some of the patterns that we know to be true with parallel lines. When parallel lines get crossed by another line, which is called a transversal, there are many things about the angles created that are the same and some patterns that we can see. So our two parallel lines here are the orange lines. We'll put the little parallel symbol there. And the transversal is the red line. And as you look at this right away, what I hope you notice is that there's really only two angle measures. In this case, either 62 or 118. Take a minute and just see kind of what kinds of things you notice by looking at those 62s and 118s. Right. Maybe you notice that the angles that are right across from each other are always the same. So these are across from each other and they're 62s, and these are across from each other and they're 118s. Maybe you notice that 118 plus 62 is 180. So we have a lot of 180, 180, 180, 180, or all the way around would be 360. Maybe you notice that the two that look like they're kind of inside the lines here are the 118 and the 62 add up to 180. Or the ones opposite each other on the inside, like if this were a Z, the ones on the inside angles of the Z are the smaller angles, and they're both 62. So there's a lot of things that you will learn, if you haven't learned already, in review, but some things that you should notice. Namely, that when you have two parallel lines cut with a transversal, there's only two angle measurements. In this case, 118 or 62, but regardless of what those two angle measurements are, they add up to 180. Now let's talk about the names of some of these angles. These angles can be made into pairs of angles which do have special names. So let's take a look at those names. The first name of a special pair of angles is corresponding angles. Corresponding angles are equal, and they're angles in matching corners. Again, we're talking about two parallel lines cut by transversal that creates these. And in this case, A and E are corresponding angles. They're both above the parallel line. So you can see if you go from the parallel line and go up, they're both above and to the left of the transversal. So A and E are corresponding angles. See if you can name a few others. Right? Hopefully you said B and F. They're both corresponding angles up and to the right. You have C and G below the parallel lines and to the left. And then you have D and H, again, below the parallel lines and to the right. Those are our 4 sets of corresponding angles, and corresponding angles are equal. Whatever their measurement may be, it is equal. Another type of angle is the alternate interior angles. These are on opposite sides of the transversal. That's why we have the word alternate, but they are inside or between the 2 parallel lines. So C and F are alternate interior angles, as are D and E. Again, if you think of this kind of like a Z, your alternate interior angles, they are the ones kind of across from each other on opposite sides of the transversal, but inside the parallel lines. Another type of special angle created by parallel lines is the alternate exterior angle. Again, they're on opposite sides, that's that alternate word, but instead of being between the parallel lines like C and F, they're on the outside or above or below the parallel lines like A and H and B and G. And alternate exterior angles are also the same when we're talking about parallel lines. Vertical angles in this case don't mean that they're up and down, it means they share the same vertex. They both have this as their vertex and they're across from each other. So E and H are vertical angles, F and G are vertical angles, A and D are vertical angles, and B and C are vertical angles. And those are all equal to each other. Remember that there's only 2 different angle sizes. So when you have a pair of parallel lines and a transversal, you've got a big angle and a small angle. In this case, A, D, E, and H are all equal to each other, and B, C, F, and G are all equal to each other. And if you add a bigger angle with a smaller angle, you'll get 180 degrees. So now that we've got maybe all of that reviewed or all of that packed away, let's take a look at some examples of how this might be useful to us. In this diagram, we have a pair of parallel lines and a transversal. It helps when the parallel lines are marked. So these 2 are parallel, and this is the transversal. And we want to know which of the following pairs of angles are alternate exterior angles. So what's the alternate exterior angle for S? Again, it's got to be alternate, so on the opposite side, so not this side of the transversal, but this side. And it needs to be exterior, just like S is. So hopefully you said that that was Z. And then the alternate exterior angle for Y, again, here's Y. Alternate of that is the other side of the transversal, so this side, but down at the opposite end. And opposite of Y, but also on the outside, is T. And those alternate exterior angles are equal. We can use our rules about angles to determine if, in fact, lines that appear straight are actually parallel. So the question is this: are the lines AB and CD parallel? They look kind of close. They look like they could be parallel. We don't have a Cartesian plane, so we can't determine the slope, but we can look at the angles. And I see that this one is 108. And the alternate interior angle is 110, which tells me no, they are not parallel because the 2 alternate interior angles are not equal. Alternate angles will be equal if we're talking about parallel lines. Now let's take a look at another example. AB and CD are parallel. You can see our parallel line marks here, these little arrows, and EH is our transversal. What's the size of angle EFB? So this is the one we're wanting to know, EFB. Well, let's start with what we do know. We do know that this is 54. Okay, so all of our other small angles, our vertical angles, are going to be 54. I could go ahead and label all those here. And we also know that there's only going to be 2 angle measures, 54 and whatever else adds up to 180. So if I take 180 and I minus my 54, 180 minus 50 would give us 70, and then minus another 4. Oh, I did that wrong. 180 minus 50 would be 130. Sorry, minus another 4 would give us 126. So that means all of our bigger angles here are going to be 126, and I do like to label all of them just to make sure I haven't made a mistake somewhere. And so I've got 54 and 126, so the size of angle EFB is that 126. A and B and C and D are parallel lines, and EH is transversal. What's the size of AFG? Now again, you see the answer right there, but let's talk about how we can figure that out. So EFG, F is the angle, it's the letter in the middle, so it's the one that I want to know about. And again, what do I know? I know that the bigger angle here is 119. That makes G 119, that makes F 119, and that makes this one across from it 119. And to find the other angle there, I take 180 minus 119, and I get 61, which means this is 61, and this is 61, and this is 61, and this is 61. And that's how I find the answer that AFG is 61 degrees. So a lot of math with 180. Here you don't have the answer right away, so let's see if you can figure it out. A and B and C and D are parallel. You see the parallel line marks. EH is the transversal. What's the size of angle? DGH. So G is the one we want to know here. DGH, the one in the middle. Well, what do I already know? I know that this is 133, so I could go ahead and label all my 133s. That one. And then alternate interior angle is 133, and that one's 133. And I know that my other angle measure, whatever it may be, has to combine with 133 to make 180. So I take 180 minus 133. So 180 minus 130 is 50, and then minus another 3 there, and we get 47. So we can label then all of our angles 47, although I'm not going to do that for sake of time, and we get 47 degrees. So again, a lot of knowledge and work with the number 180, not just in triangles. Here we're told that S and T and U and V are parallel lines. We've got our two orange parallel lines, and we've got a different type of angle now introduced. Angles that are not equal, but that add up to 180. Are consecutive, that means one right after the other, consecutive interior angles, because they lie between the parallel lines and they're on the same side of the transversal, that's why they're called that, and they add to 180. So C, you can tell, is our smaller one, and E is my larger one. Those add to 180, as would D and F. Right, we have our vertical angles here across a shared vertex with the same measure. Our vertical angles are G and F. D and E are, see if you can tell what kind they are. D and E, they're on opposite sides, so we know I have the word alternate, and they're inside the parallel lines, alternate interior angles. We can also use what we know about lines to solve for variables. So in this case, P, Q, and RS are parallel, TW is the transversal, and the size of angle TUQ, this one, is x plus 12, whatever that x may be, and the size of angle SVW is 3x plus 48. We've got a bigger one and a smaller one. They're on alternate same sides, which tells us they add up to 180. So we can create an equation that x plus 12 plus 3x plus 48 is equal to 180. We then combine our like terms, and we get 3x plus x is 4x, and 12 plus 48 is 60, equals 180. We then isolate the variable term by subtracting 60 from both sides, and we get 4x equals 120. Finally, we isolate the variable by dividing by 4, and we get x is equal to 30 degrees. Now we want to solve for a variable and then go back and plug it in. And I'm running short on time, so I'm going to talk quickly here. These two angles, again, we know will add up to 180, so we write our equation. We combine like terms. We isolate the variable term by adding 48 to both sides, and then we isolate the variable by dividing by 3. What we get is that x is 76. But the question is asking what's the actual size of FGD, this one right here. Well, if this is 2x minus 100, then this is 2x minus 100. And we know that x is 76, so let's plug and chug. And we get 52 degrees. All right, I'm almost out of time. I'm going to talk quickly today. We interpreted parallel, perpendicular, and intersecting lines. Plus, we determined the measure of vertical angles and other special angles created by parallel lines. Make sure you guys write down any questions you have, and I'll see you next class.